Today our speaker is Gennadiy Navrotskiy with some properties of cross-sections of Gaussian random fields. Please, Gennadiy.
Oh, yes, thank you. Oh, yes. Yes. So, the work is devoted to investigation of the asymptotic behavior of the number of upcrossings of the fixed level C greater than 0 by certain Gaussian random process. Process is stationary, periodic, and has almost surely continuous trajectories. The process is constructed using smooth Gaussian random mapping from R2 to R3. So, and our interest lies in the asymptotics of this characteristic of number of crossings when R, the radius of our circle, increases to infinity. Yes. The interest to such random fields and their characteristics is motivated by paper on a stationary random node by Navrotskiy, in which the following model of Gaussian random curve was introduced. Let us consider the stationary centered Gaussian random field on the plane R2 with values in R3. Yes, so its coordinates are independent, identically distributed, then let us define the random closed curve in space R3 as the image of the unit circle S on the plane R2 under our mapping psi. So it was proven that with probability 1 such random curve has no points of self-intersection. Therefore, it is a random curve. Yes, so the model in our study is similar. We construct closed random curve using Gaussian stationary random field Xi, which is with independent identically distributed components, which are also well centered and yes, and stationary. Then we consider the image of the image under the mapping Xi of the circle S with standard parameterization R cosine t, R sine t. We have here an example of realization. Yes, on the image we have an example of realization of Xi, sorry, eta R in the space R3. Yes. Our immediate aim is to investigate the asymptotics of process eta R when R goes to infinity in the weak sense, and check if there exists a limiting process and whether there will be a weak convergence to such a limiting process. So the covariance, yes, under parameterization R sine t, R cosine t, our covariance of the components of Xi yes, not Xi, but eta R has the following form, and it is periodic by Ts, and so has no limit when T minus S converges to infinity with fixed R under fixed Ts such that absolute value of T minus S not equal to Pk. There exists a limit for the covariance of the components of the process eta. And the limit is 0, and since our values eta r are Gaussian, we can conclude that with large values of r, the corresponding values eta r of t, eta r of s become almost indefinite. This well can be explained since with increase in r, our circle also grows, and so the images of Ts also become yes, the distance between images Ts becomes very large. So then we modify the process to obtain smooth limiting covariance of the covariance function. So zeta r is the modified, yes, is the first component of the modified of process eta r. Is not important which component to take, because they are all independent, identically distributed. So yes, and we obtain the limiting covariance function for these components such that it is infinitely differentiable, where R converges to infinity. Yeah, so in the next part we can we define the characteristic of this random process zeta R of t that we will try to find the asymptotics of, and the motivation of is, yes, so first we define the approaching point, and the approaching point for the OC greater than, yes, for the OC in R by the function f is such a point t that f prime t greater than 0, f of t equals, yeah. So why do we use approximate? Because the number of upcrossings is linked to certain not invariants, and so our test for the number for upcrossings is motivated by that. Yes, so one of those not invariants is tricolorability. So the tricolorability is defined in the following way. Let us take every arc between two under crossing points of our node, of the diagram of our node, and assign one of three cores to each such arc. Yes, so then node will be recorable if each crossing only has one or three the different cores, and the recorability is invariant, is not invariant since it does not change under Riemann moves. We have an example of recorable node. It is well, relatively simple example. It is a trefoil node. Yeah, so next, before we will establish whether the limit of the number of crossings of the OC exists by our process zeta R. Yes, we need what we need is to find the sufficient conditions for convergence of the number of crossings on some interval is 0t for deterministic function. Yes. So, and such sufficient conditions are if we have a number of sequence of continuously differentiable functions, and with such that they all start 0 when t equals 0, and they also converge uniformly to some continuously differential function f on the interval 0t, and this is also they should also converge with their derivatives. F is such that for such that there is no points t in 0t, such that f of t equals c, and f prime of t equals to 0, which means that we can only have well, for the level c fixed, we can only have points of up crossings or the points of under crossings correspondingly. And then we can conclude that the number of crossings for fixed level c greater than 0, it has a limit. And this limit is equal to the number of crossings of c by our function f. In order to prove it, well, since we know that our function f is continuously differentiable, and therefore if f g converge to it with their differentiables, we can always find for every point of approaching the neighborhood of tk with radius theta k, such that f prime of t will be greater than 0, and due to uniform convergence of derivatives prime j, we can also find such number m that absolute value of prime j of t will be greater than 0. Therefore, we can only have points of in each such neighborhood tk and delta k. We can only have the points of up crossing or the points of under crossing. If it is yes, so if our function f is increasing monotonically in the neighborhood b, then we can find local infimum and supremum. Then once we choose f m m such that fm and ft are close enough, we ensure that the function fm is m large enough crosses the level c. Yes, so we have the point of crossing. On the other hand, we have to prove that there can be any other points of crossings outside of our set b, tk, delta k. And well, since our function f is continuous, and there is by conditions our theorem and no other points crossing by the function f, then we can conclude that there is minimum of ft minus c, which is greater than 0 on this compact set. So therefore, and since f k fn converge uniformly for function f, we can conclude that they will also converge, and since some n, this value f n minus c will be greater than some epsilon greater than 0. So then our next point
Okay, is he disappeared?
Yes.
Okay, let's wait. It happens sometimes with his connection. Mm. I called him, but without answer, so I propose wait 2 minutes and then we will stop our session because of technical reasons. Okay, unfortunately, Gennady is
He's
disconnected
here.
now. Oh, okay. Oh, Gennady, hopefully you are here. Mhm. I cannot see him.
He joins the audio.
So yes, I apologize for
Okay, let's continue.
yes.
Mhm.
Let us continue. So previously we found we discussed the sufficient conditions for convergence of the number of approaches for deterministic functions, and so now we return to our Gaussian random process zeta r. Yes, so what we are going to find is that there exists a weak limit of zeta r as r converges to infinity, and moreover the zeta r zeta r prime, its derivative also converges to zeta prime infinity. So how we prove it, since processes, since the process zeta r of t is Gaussian, we can conclude that from the convergence of covariance function, we have the convergence of finite dimensional distributions. But that doesn't prove weak convergence. For that, need conditions on the boundless moments, conditions for the modulus of continuity. Then how do we? Yes. So then we have, yes, so we have for large T and S, since we already have the, such expectation, zeta T minus zeta R squared is continuous and bounded by Ts and even periodic by Ts, then for large values of T minus S, we have such inequality, and then we, what we need to prove is to prove this inequality for small enough T minus S. And for this we use the known inequalities for sign and for exponent. So for the derivative is for the derivative of beta r. The proof is similar because it's also periodic, this expression, and continuous, therefore bounded. We only have to prove for small enough t minus s, and for such t minus s, we use because when t minus s converges to 0, we can use Taylor expansion. So then, if we have our inequality with some b, beta lesser or equal than 1. So yes. So our next result is that we find averages of the number of operations by t by r when t converges to infinity. So since well, in other words, we find that the number of approaches when averaging by parameter t has we obtain the same values as when averaging over our radius r almost surely. This equality holds because due to periodicity of our zeta r, we have that u zeta number of operations are equal for each interval zeta for each interval 0r and k r k plus 1r, and also our number of approachings is strictly monotonic function as well relatively to the length of our interval 0t. Therefore, we have such convergence. So next. So since our aim is to in this part of our study is to find the asymptotics of the number of operations for the limiting random process zeta infinity, we need to find formula for its expectation. So here we have the formula or the expectation matrix theorem, which allows us to express the expectation of the number of such points in parameters set t by using the joint density of f of t, number f of t, and g of t. So and this integral has well, since number f has n plus 1 components, and B has k components, therefore we iterate over R to the power n plus 1 over 2 plus 3. Yes. So then we need to establish the conditions under which the expectation meta theorem holds, and in the case of centered stationary Gaussian random processes F and J, such sufficient condition have relatively simple form. So yes, such those conditions are needed to guarantee that the F number F and G have almost surely continuous trajectories, and that models of continuity F converges to 0. So then so we have such formula where C I of J is the covariance function of derivative of derivative F J, and S E C E J is covariance function of process G, and we have to prove such relation for some k greater than 0, greater than 0, and small enough t minus. So yes, since we know the covariance, we can evaluate once again the proof is similar. So we again can use Taylor expansion, and then we only have to prove that t minus s squared is less equal than by t minus s to the power of minus 2, and t minus s converges to 0. So we can conclude that such condition holds. We can indeed use the expectation meta theorem for process zeta infinity. So how do we use it? Is that as we mentioned, as we found out in the previous lemma, for the sufficient condition for the convergence of number of approachings for deterministic functions f, it is that the limiting function f has no points such that f of t equals c and f prime of t equals 0. So we need to prove such relation for our process zeta infinity. So yes, for that we will consider our new random variables, and zeta infinity depends on 3 arguments 1 over n c and t, and it is just the number of points t such that zeta infinity of t equals c, zeta infinity prime of t is lesser than 1 over n. So we use to calculate the expectation of such points, we can use our expectation meta theorem and see that it converges to 0, converges to infinity. And since such random values are non-negative and decreasing, we can use the monotone convergence theorem you see that the expectation of n0 of our number of those points where zeta infinity of t equals c and zeta prime infinity of t equals 0. Its expectation will also equal 0. And since this 0 is non-negative random value, we can conclude that is probability 1. It's probability 1, there is no such points t. Yes, so once we found out such relation, we can proceed to try to prove that we have limit in distribution for the number of upcrossings by the process zeta r of the level c when r goes to infinity. To prove it, we use Skorokhod theorem. So if we have zeta r convergent distribution, then we have also some kappa r converging with probability 1. But if kappa r converge with probability 1, then we can apply for its trajectories our lemma for the convergence of the number of crossings, and therefore the number of crossings by the process kappa r must converge to some number u kappa infinity, and since zeta r and kappa r are equal in distribution, then there also exists a weak limit u zeta r. Yes, so and in the next result is that we look for the asymptotics in the mean square for our for the number of crossings by of limiting random process zeta infinity over the interval to pk to pk plus 1. So it is interval with length 2 pi. Yes. So if we average the sum of such the sum of such random values over t, then we obtain just its expectation in the mean square sense. So in order to prove it, we use we can represent this sum of squares, and then we apply for the covariance of uk infinity k plus j infinity the expectation meta theorem to calculate its expectation. Oh yes. So and to prove it, we then find the inverse of covariance matrix, and we find that it is the following form A of e to the power minus t minus s squared, and A where A are some constant matrices, and k k, and O is the same order as e to the power minus t minus s squared. So therefore, we can conclude that when g converges to infinity, then since t minus s also then goes to infinity, then s of j converges to 0. And our next step is to use the Chopin theorem. And since such partial sums of t minus with value j converge, then if we multiply them by j and sum again, they should converge to the limit of s of j, which is 0. So the whole sum converges to 0, and we have the limit in mean square. So yeah, that's all. Thank you.
Okay, thank you very much for your talk. Maybe somebody have questions or comments, please.
I
Can I
have a
ask a
question.
question?
Yes, please.
Thank you very much for a nice talk. I have a slightly side question. So you use Gaussian covariance function. So if you consider other types of covariance functions, especially maybe a case where covariance function is non-integrable, then you introduce maybe strong dependence between values of your processes over distances. So do you know something about these cases?
Well, in our case, we can use expectation meta theorem because our conditions for it are have such form Gaussian case, but for other covariance functions they have different forms. So I can say about that.
Okay. And maybe another comment. So you consider it like random field, which is Gaussian, but of course people interested in many cases in non-Gaussian cases. So what you can do, you can just transform your vector field. Your vector field consists of 3 components, but definitely you can consider more components, and you can just apply some transformations, for example, to construct new random fields which are not Gaussian and consider similar problems. So somehow then you may translate your results, which you already have for Gaussian case, to some other types of random fields without maybe big efforts to consider some non-Gaussian distributions and other things. So this is just suggestion.
Thank you.
Okay. Some other comments or questions, please?
Yes, can I ask a question?
Mhm.
So my question is about last theorem. Before that, we were studying the symptotic behavior for R if R tends to infinity. But
Yeah.
in the last theorem, we do something different. So I was wondering what was the idea behind that and how it is related to, because it seemed just, I don't know, maybe some kind of ergodic theorem. Just it's not the same that we were studying.
Well, it's sort of the same, just that we notice that when t increases and when our number of point when number t increases, so the distance between points ts increases, they become almost independent. But if we used R, then we would have of periodicity, and they won't be becoming independent. So queens not necessary go to zero, so we won't be able to apply it.
So this is just a property of the limit that you study, right?
Yes.
Oh, okay.
Okay, thank you. Some other questions, please? I also have questions, Gennady, as I think we remain this question unstudied. Can you connect this statement with the Novak results of Sergei Novak about some Poissonian approximation of such number of approaches or so? When this constant C can vary?
When constant C. Well, I really think that C and R should have the same order rows, but no, I can't say really precisely.
Okay. I think that we will continue studying of the geometrical characteristics of these fields related to the random mode which they modeled for us. So thank you and looking for the next step. This is the end of our work in this semester. And first of all, I wish all participants of the seminar Happy New Year. And at the beginning of the new year, you will get a letter from Georgy Ryabov with the announcement of new semester and proposition to send us the titles and abstracts of your talks. So thanks everybody, Happy New Year and bye.
Okay, bye. Happy New Year.
Thank
Bye.
you. Bye.
Be healthy, guys.
Thank you, bye.